Good morning, good afternoon, good evening. Thank you everyone for joining this morning, and we are really excited that we are on our day 2 of the 3-month hands-on certification program in Pharmacometrics and PKPD modeling using R, S, and LME. As you are all aware that this day, following the day 1 of the talk, we had some homework assignments that were shared with the participants, and many of you have already worked on it or are currently working on it. Thank you to all who actually have been diligently working on the assignments. And today we have Serge back with us. He would help in addressing any questions or any doubts that you have with regards to homework assignment. And again, we would strongly encourage for you to ask questions. And once we have covered the homework assignment, Serge will actually walk us through, bring us to the next level of understanding with pharmacometrics, and would also be covering a few additional topics. Right now, I see that we have about, close to the number that we had last week with regards to the participants. Again, really excited to have you all back for your day 2 of the workshop. I would, a few other logistics. If you have any questions, please use your raise hand button on your screen, and one of the coordinators here, either Arun, I, or Fatima, will unmute you. So you will get an opportunity to ask questions of Serge. We also request that you are able to come on video when you're asking the question, so we can actually get to see you and get to know you as well. For any reason, if you're not able to ask question directly, please put your questions in the chat box, and Arun will actually read the questions so Serge can answer them for you. And if you have had any other issues in terms of access or all of that, we will address the logistical parts of the question at the end of the workshop. Unless there is something which is really important and burning that needs to be addressed right away. Any other logistical questions we will address at the end of the workshop. Again, thank you all for joining. Now I'm going to stop sharing my screen, and Arun will actually start presenting the homework assignment so we can start discussing the answers point by point. Arun, do you want to start with reading question number 1, please?
Yeah, sure. The first question is, at the first scenario, a single IV bolus dose of 100 nanogram is given to 4 patients under 4 different occasions in a crossover trial. So the predicted concentration time profile is given by the following equation, where C is the predicted concentration, V and Cl are the volume of distribution and clearance respectively. K is the first order elimination rate constant, and T is the time since the dose was given. The observed concentration Cops is given by the equation Cops is equal to C plus epsilon, where epsilon is from a normal distribution with mean 0 and a standard deviation, where epsilon is a sample from a normal distribution with mean 0 and standard deviation. Each occasion corresponds to a different formulation of the same drug. On each occasion, observed drug levels are recorded for 24 hours. We assume full washout between each occasion. The plot for the 4 individuals grouped by occasion is shown below. So we have 4 different plots for 4 different patients, with each color indicating different occasion. So the first question for the scenario 1 is, can you see any variability in volume of distribution? If so, explain.
So I would like to actually have one of you volunteer to help address this question. Who would like to go first?
Some coordinators or team leaders can also pitch in, no problem. So whatever, I think many of you have submitted your answers. Please raise your hands and they will unmute and you can explain the first question. Somebody?
Well, if you don't actually volunteer, then maybe, the Ravi Shah would like to answer the question. So Arun, Ravi, it will be great if you actually raise your hand. That way we can actually identify you and you can be picked to answer the question. Arun, were you able to find Ravi?
No. Since I'm sharing the screen,
Got it. Okay, let me try to find Arun. So I would really appreciate if you can raise your hand. We can identify you faster. There you are. You are unmuted, Ravi. So if you can get on video, that'd be awesome. That way we will get to see you as well. If not,
means I will try to start the video. I'm not in a position currently, but
that's fine. No worries. Go ahead. Go ahead, Ravi. The floor is yours.
Yeah, so in this question, can we see any variability in volume of distribution? And the answer is no. The volume of distributions is same as the concentration is same, which is I think nanogram per ml, and everybody has the similar or a same 100 nanogram per ml as a volume of distribution. So we do not see any variability in volume of distribution.
Thank you there, Ravi. Serge, would you like to add anything more to what the answer that Ravi gave?
No, it's correct, exactly correct.
So as you can see, though the question was pretty long, the answer was pretty simple. Thank you, Serge. So Ravi, Arun, can we move on to question number 2, please?
So moving on to the question number 2, what is the best estimate for volume of distribution for each of these patients? We have a dose of about 100 nanograms, and the concentration observed is 100 nanogram per ml.
So Arun, I see that somebody put, okay, we have Simone Davis who's helping answer the question. So Simone, are you able to raise your hand so we can actually have you answer the question verbally as well?
The answer is correct.
Yeah. So this is Simon. I don't know if you can hear me now. Maya, I think the dose was 100. Sorry, the oh no, I've probably got this wrong now. I'm looking at it again. The dose was 100 nanograms, right? Ah, yeah, but my maths is incorrect. Yeah. So then the concentration was 100 nanograms per mil. It should have been 1 mil, not 100 mils. Sorry, error. But yeah. So the formula was right. The answer was wrong, I think.
Mm-hmm. Yeah,
So
you just need to. Yeah, just pay attention to the units, but that's not the most important.
Yeah, I just read the plot.
Just to remind you that the information at t equals 0, especially for IV, will give you direct information about the volume of distribution if it's an IV bolus, and that was just the idea here. And there's no variability, and we can estimate correctly the value of the volume. Now, the reason I'm saying estimate is that with real data, you will have some fluctuation because of the error model, and then you will have just an estimate of the volume. And here, the best estimate is just by applying the equation, concentration is equal to dose divided by volume, where t equals 0, the exponent disappears, and then you can retrieve the volume of distribution, which is equal to the dose divided by the initial concentration. And then if you apply the unit correctly, then you can find the volume.
Okay. Shall I stop my video then?
Yeah, then we can go to the next question.
Moving on to the third question. Is that the variability between occasion for each patient due to the variability in volume or clearance? Explain.
Thank you.
Then here, obviously, you don't have any choice. Okay, then the answer is correct. I just see the shot, then I don't hear anybody. Then let's go to the next question. Obviously, because we already conclude that there's no variability in volume, and we still see variability between patient and also between occasion, then it has to come from the second parameter, which is clearance.
So the fourth question, for the selected parameter that exhibit variability between occasion, can you decide if the variability is due to a formulation effect or just a between occasion random effect? We assume here that only one of the two options exists. There is no combined formulation effect and between occasion variability.
All right. Manasa, I have seen your hand up and I thought I tried to unmute you. Okay, let me unmute you again. Please accept the prompt.
It's due to the occasional random effect.
Say that one more time, Manasa.
I beg your pardon. Yeah.
Repeat yourself, please.
So it's just because of the intra-occasion random. Yeah, it's, can you hear me? Yeah, can you hear me?
Yes. Yes.
Yeah. The variability in the clearance is just because of the occasion random effect. There is no formulation based effect here over here. This is my answer.
And what's the reason?
Okay. Yeah, okay.
To help you, in other words, I told you that it's either or either.
Yeah.
Then yes, because from the data it could be both, but it's really either or either. I mean, you can have a small fix. I mean, when you are talking about the formulation effect, it's a fixed effect. it's a trend.
Yes.
And what does that mean? The trend is that we would see that one of the formulation systematically has, let's say, a lower clearance. You could rank order basically the clearance. Now, if you rank order the clearance here for the 4 patients, what do you see? Do you see a trend or do you see something random?
It's something random over here.
Correct. And how do you see that? If you just look at the color and you can see, let's rank order the clearance for each patient separately, okay? Then basically what we can see for patient 0, red, orange, green, blue. That's right?
Yes.
Order. Then for patient 1, we see yellow, red, green, blue. Then for the patient 2, green, blue, red, yellow. And then the last one, you can see green, blue, yellow, red. Then basically there's no trend at all. It's completely random.
Right.
And that's what differentiates. If you have a strong fixed effect, you should expect see most of the time a certain ranking. And that's basically the right answer. The new answer was right. It's just that it's important to explain basically from the data. And use of the color, it's something that helps a little bit because you can write down the rank of the clearance for the 4 patients. And then you see there's no specific order. I cannot see systematically, I see red larger than yellow, larger than green, larger than blue. It's not correct.
Right.
It changes all the time randomly. Now the reason I say that it's either or either is because with real data we can have a combination of a fixed effect, a trend, and in addition you can have also a random effect, interrotation random effect. It's possible, and there are statistical ways to test that, or at least the fixed effect. Okay.
Yes, thank you. No, I clearly understood. Thank you so much.
Okay, what's the next question?
Moving on to the next question. So can you write the equation for both clearance and volume structural parameters?
Okay, who is volunteer?
So we have Mansa again, who would like to answer the question. We would like to give those of you who have not shared yet an opportunity to share here. I know many of you have completed this homework assignment, and again, I want you to be aware that there's nothing wrong in giving a wrong answer too, because that's how we learn.
Yes, sometimes a wrong answer is even better than the right answer. And the reason is if you have a wrong answer, then I can explain something. If you have the right answer, then it's just say it's correct. It doesn't mean that you need automatically give me a wrong answer, but at least you should not be afraid to propose something and maybe it's not the right answer. The idea here of the question is that we learn together the different components, how we can write the equation for a structural parameter. And we have different components. We have the fixed effect, which is basically if there's no covariate, it's the average. We have the between subject random effect, and then we have the inter-occasional random effect. Now, sometimes we don't have between subject variability. Then you should be able now to write down the equation for both the clearance and the volume and see what's the difference in the equation. Then I see 2 participants raise hands. And Aruna, you can select randomly. Or somebody that didn't answer.
Sure.
Yes.
So I think, yeah, go ahead, Nilesh.
Yes, and so it's pretty simple for volume because here there is no variability in the volume. So volume is V is equal to the typical value of volume, and all the variabilities will be 0. When it comes to clearance, since we have occasional variability, we will have clearance CL is equal to typical value of clearance multiplied by the exponential of the eta clearance, which covers the inter-individual variabilities, and then you multiply by the exponential of clearance for different occasions. Here in this case, it will be four different occasions that we need to multiply for clearance. So that should be the structural formula for clearance and volume.
Okay, that's correct. Then what we learn from here, which is different when you write the equation, when you have a fixed effect, a covariate relationship, is that here for each occasion, we have an inter-occasional random effect, which is a sample from a distribution that has a mean of 0 and a certain variance that we call the inter-occasional variance. And because we have 4 occasions, we have 4 products. Remember that when you have a fixed effect, that they have different levels, we have 1 degree of freedom, and we are going to see this in the maybe in the next question. I don't know. I do not remember what question I asked. And remember that here we have basically 4 products. Okay, very good.
The next
if somebody
question.
doesn't understand anything, just ask me the question. That's the right time to ask.
Go ahead, Arun. We can move to the next question.
So what kind of error model do we have here in this scenario?
Who want to answer? Okay, there's a.
So we have.
There's the wrong answer, and that's okay. Then let me ask you the question. Let me ask you the question differently. Why can somebody explain why the error model is not additive? What's the difference between additive and multiplicative?
I think Avinash, you have been unmuted, if I'm not wrong. Let me unmute Shyam. Please accept the prompt, Shyam.
Yeah, I accepted. Am I audible now?
Yes.
Okay, so here the error from the equation we can see it is an additive residual error model. So the difference between additive and multiplicative residual error model is the difference in the concentration will be constant at the lower range, and in proportional it will be higher at the higher range. So to match that, we will add additive and proportional error model.
Okay, let me ask you the question. Remember one thing, that the figures that I gave you were just to show you the trend. There's another tool with data. And the answer, it is basically in the definition of COPS, which is in the text. And you can see that COPS is equal C plus epsilon. And epsilon, it's a sample from a normal distribution that has a mean of 0 and a standard deviation that is equal to CV multiplied by C, where CV is constant. Then the standard deviation here is proportional to the predicted concentration. I know that we don't see this really in the data because the data were just visual, but that in the text it's written that we have CV multiplied by C. That's what I meant. Then in that case, since the standard deviation is proportional to the predicted concentration, we are talking here about a multiplicative error model. And don't pay attention to the data. That data are just to show you the difference between the predicted concentration. So this is really predicted concentration. It's not. I didn't show really the real noise here. Is it clear? Okay, I will explain again.
Yes, it is clear. Yeah.
Okay, but I will explain to somebody that asked to explain again. You don't see in the data, but COPS, what is COPS? If I would take a patient and I would do the experiment 1,000 times at the same time, what I would see is that I would get 1,000 different observation value. And suppose that I'm starting at a low level, low concentration. And then I'm doing 1,000 times the same experiment, and I see that the average concentration is 1, and I see that the standard deviation is 0.1. Okay. Now suppose now that I'm going at a higher level, and the level is 10, and suppose that the standard deviation is 1. Then what I see is that the standard deviation increased at the same rate like the predicted concentration. When the standard deviation of your observation, because the observation is random variable. Why it's a random variable? It's because if I would do the experiment 1,000 times, I would get 1,000 different value. And COPS, which is what I have in my data, is just a sample from all the 1,000 observation I would get if I was able to redo the experiment 1,000 times. But I just got one value. Then COPS, it's a random sample from a distribution. And if I'm telling you that the standard deviation is proportional to the predicted concentration, which is what is written here by CV multiplied by C. CV is a constant, it's called the coefficient of variation. For a good assay, it's a 0.1, 10%. But you can see that if C is equal to 100, and let's say that CV is equal to 0.1, the standard deviation is equal to 100 multiplied by 0.1, which is 10. If C, the predicted concentration is 1,000, and CV is 0.1, then the standard deviation is 100. Then you can see that the standard deviation of your observation increased proportional to the predicted concentration, which is exactly the definition of multiplicative error. If I would write N0 and then SD being a constant, it would be an additive model. If I would put, instead of putting SD is equal to CV multiplied by C, I would put SD is equal to constant, then it would be an additive error model. Is it clear now?
Thank you, Serge.
Now about somebody asked a question and you are right about the question. I just write. I just. Can you go up? Can you go up where I put the equation? Yes, here. Yeah. Then basically, I didn't write the code that you would need to write. Huh? That you would need to write basically if you would write the Phoenix modeling. Huh? I just explained that epsilon is a sample from a distribution that has a mean of 0. Huh? And basically a standard deviation equal to CV multiplied by C. It's true that you can write the equation, and that's not the purpose here. You are going to learn the Phoenix modeling language. Then what I wrote is correct. Huh? The standard deviation is proportional to the predicted concentration, and you can write basically you can write this in a different manner, like the person put in the chat, but that's exactly the same thing. In other words, you can put this, you can put basically the CV outside the normal distribution. That's not really important. In other words, there are different ways to write the equation.
So Arun, I see that there were a few questions which are in the chat. If they are relevant, can we answer those questions, please?
Sorry, Arun, I won't. I can't see the chat panel when I'm sharing my screen.
Okay, so, got it. Rajan, can you go through if there is anything that needs to be answered here? And participants who have actually put the questions in the chat, I would strongly encourage you to raise your hand so we can actually unmute you so you can ask the question.
Can I share my screen 1 second just to show to answer the question?
Absolutely. Arun, if you can stop sharing. Yeah.
Once again, and basically, then you can write the equation. I think that was the question basically here. One way of explaining is what I explained it. That's basically we have basically the standard deviation as a mean of 0, and the standard deviation is equal to CB multiplied by the predicted concentration. The epsilon basically here we have basically another way to write down that it's C ops is equal to C multiplied by 1 plus C epsilon. The difference is that basically in that case the C EPS is a normal distribution with a mean of 0, and the standard deviation basically is it's your coefficient of variation. For example, if it was 0.1, this would give you a multiplicative error model with a 10% coefficient of variation. And that's the other way. I think that's one of the person in the audience who wrote that, which is basically, I think he wrote that C plus basically C multiplied by C EPS. But pay attention that CEPS has a different meaning. Now basically it's a mean of 0, and the standard deviation is equal to a specific value, not CB multiplied by C, because I put the C outside. Is it clear?
Thank you, Serge.
Hi, Serge. Somebody asked a question like, can you tell a practical situation we had to use this additive error model, and in which situation we'll be using multiplicative error model? Some kind of in situations or scenarios we had to use this different model. That was one of the questions.
I understand the question. In reality, most of the time when you have pharmacokinetic data and you have different cohorts going from a low dose to a high dose, you are going to have concentration that go to very low level to very high level. In that situation, most likely that you are going to use a multiplicative error model, because, for example, you can have observation equal 0.1, 0.31, and you have also observation that are in the range of 1,000 or 10,000 or 100,000. If really the error was about, it's about 10%, then you understand that when you go to 1 million, in reality, when you have 1 million and you compare the 1 million compared to 0.1, there's no way that the error can be the same for the very large value and the very low value. Because if the error was the same, and for the 1 million value, you have an error of, let's say, 1,000, there's no way you can have an error of 1,000 and the same observation that is a value of 0.1. And when you have very large range of concentration, you use always multiplicative. When you have very low dose that lead to very low concentration, you can use also the combination of additive and multiplicative, which means that at low concentration, you will have a residual variability that it's not anymore proportional to the predicted concentration, but that's basically the assay error that always exists. Then you can try first multiplicative. If a problem with multiplicative, you can do additive plus multiplicative. You are going to learn also how you code that. Additive, most of the time, that's where you have pharmacodynamic data. And the reason is pharmacodynamic data spend over a very lower range of value compared to what you see in PK. Suppose you have C-reactive protein and you have inhibition of the C-reactive protein by a drug. Then instead of going from when you start, let's say, at a level of 100 and you have 50% inhibition maximum, then you are going to go maximum from 100 to 50. And then you are going to get data from 50 to 100, which is a very low range. And because it's a low range, then it's enough to use additive. There's no really change in the standard deviation. From a practical point of view, additive is easier to handle numerically when you basically optimize your model, when you try to optimize the estimate. Then, in summary, when you have a small range of your data then you can start with additive. If you have PK data, most likely that you are going to use always multiplicative because pharmacokinetic data span over a large range. Now you cannot do a statistical test and compare additive and multiplicative, and again, it's outside this topic. But once you look at the diagnostic, there are some diagnostic that can help you to make also the decision if you have additive or multiplicative. When you compare the observed versus individual predicted concentration, and you see that you have more noise in the plot DV, which is your observation, and I-Pret, which is your individual prediction, and you see that you have more noise, more fluctuation around the y equal x. If you see that at large concentration you have more fluctuation, then apparently it's multiplicative. If you see that the noise has the same variance independently of the individual prediction, then apparently it's additive, which most of the time will not happen with PK data, but can happen with pharmacodynamic data. Arena, I think you can kick me out of the share screen. I don't know how I can. Stop share. Okay, stop share. Okay, that's it.
Thank you, Serge.
You're welcome. You can continue if there's still something.
So moving on to question number 2. Arun, can you walk us through?
So we have question number 2. It's a similar case scenario. A single IV bolus dose of 100 nanogram is given to 4 patients under 4 different occasions in a crossover trial. The concentration time profile is given by the equation, where C is the predicted concentration, V and K are the volume of distribution and first order elimination rate constant respectively, and T is the time since the dose was given. The observed concentration, Cops, is given by the equation Cops is equal to concentration plus epsilon, where epsilon is the sample from a normal distribution with mean 0 and standard deviation, where standard deviation equals the coefficient of variation multiplied by the concentration. Each occasion corresponds to a different formulation of the same drug. On each occasion, observed drug levels are recorded for 24 hours. We assume a full washout between each occasion. A plot for 4 individuals grouped by occasion as well as the same plot but grouped by patient are shown below. So we have 4 different plots based on different patients, and we have 4 plots based on different occasions. That is for 4 different formulations. So with this, we have the first question. Is that variability between occasion for each patient due to the variability in volume or K? Explain.
Any volunteer?
Am I audible?
Yeah, go ahead.
Okay. In this, the variability is due to the volume of distribution. That is, from the graph, we can observe that the slope is same for all the 4 occasions, which means there is no occasional random effect in the elimination rate constant.
Okay, this is correct. Then again, what do we learn from here is that the plot have been shown in the log domain. And that's very important. You can see the plot on the 4 different occasions, the y-axis in the log domain. Since it's a 1 compartment IV, we know that basically we only 1 slope. But what we can see is that basically all the slopes for the 4 formulation are parallel one to the other. And since the slope allow you to define what is the rate of elimination, then we see that slope are the same. And then therefore, basically, we know that K is constant, the elimination rate is constant, and the variability between occasions is just only due to the volume of distribution.
The second question, for the selected parameter that exhibit variability between occasion, can you decide if that variability is due to a formulation effect or just a between occasion random effect? We assume here that the only one of the two options exists, no combined formulation effect and between occasion variability.
Any volunteer?
So we have quite a few people who have raised their hands. So I'm going to unmute you. I would request that when you get a chance to speak, if you can please introduce yourself as well.
Hi, good evening. Hi, good evening. This is Ritika. I'm from Chandigarh, India. So for this answer, I think that it is due to the formulation effect. As we can see that there is a trend following for every patient and for every occasion. So this eliminates the possibility that it is the variability is due to the slope. So so I think that this is following the variability is due to the volume of distribution, not due to the slope, not due to the kinetics, elimination of the drug.
Okay. Okay, good. Then basically here we can see that we have a formulation effect and that there's no between occasion variability, which is a little bit the opposite than what we saw in the first question. And that was all the idea of this homework, is that when you have real data, are you able just visually to make the decision about what you think can happen with data? Do we have just a fixed effect? Do we have just a bit interoccasional random effect? Do we have a between subject random effect? And all this can be done by just looking at the data. It helps you doing the modeling, making some initial assumptions that can help you to come up with the optimal model at the end.
Yeah.
Okay, thank you very much. Then the next question I think was, can you write the equation for both K and V structural parameters? I think that's the last question. Then any volunteer?
So Shyam, I'm actually asking you to unmute if you can accept the prompt.
Yeah, am I audible now?
Yes, we can hear you. Go ahead.
Yeah, so the third question, does K exhibit any type of variability? Explain. Can you write the equation for both K and V structural parameters? Yeah, as we discussed earlier, there is no variability in elimination rate constant because the slope is same for all the patients. So there is no variability in the K. So when we write the equation for both K and V structural parameters, yeah, for K, for elimination rate constant, we have the typical value into the multiplied by exponential of eta. And then for volume of, here there will be no interlocation variability. For volume of distribution, we have a typical volume of volume with the exponential of eta volume, then multiplied by each occasion variability.
Then what's the equation for the volume? I just cannot.
Yeah, for volume, we have a typical volume of distribution with the multiplication of eta, exponential of eta, and then again multiplied with the between occasion random variability.
Then, but here we have a fixed effect. We have an effect which is not random, which is a formulation effect. And we have 4 formulations. Then what will be the equation that that explain the formulation effect?
Yeah, then we have to add the formulation effect, not the between occasion random variability.
I'm trying to see where is the zoom. I don't know what's going on here.
So Serge, yeah, if you would,
okay,
yeah, if you'd like to share your screen, Arun has stopped sharing right now.
Okay, and here, okay, the first thing is that I could not really hear what you said, but let me explain what we have here. Basically, we didn't have any random effect for the elimination rate because basically we can see that slope was the same all the time. Then basically we could write just k is equal to tvk. There's no between subject random effect, and there's no inter-occasional random effect. On the other hand, for the volume, we know that we have the volume that's changing between the patient, which is we have the typical value multiplied by exponent NV, which is the between subject random effect, because each patient has a different volume. But now we have also the effect of the formulation, which is a fixed effect. And remember that when on the first session, I explained how we can write the fixed effect when you have different categories, different levels. We have basically 4 formulations. Then we need to write 3 products because we have 1 degree of freedom, which is difference between a fixed effect, if you want a covariate relationship, which is the formulation effect, which is a fixed effect, where we have 1 degree of freedom. And if we have inter-occasional random effect, we would have 4 products. Then the way to work, because you have occasion 1, 2, 3, and 4, usually when you use NLME, and I guess that we do the same thing with the RNLME. If you have 4 occasions, you do not write the product for the first occasion because it's basically embedded in the what is called the intercept, the TVV. Then you have the typical value multiplied by exponent NV, where NV is a subject specific between subject random effect. And then you have the effect of the formulation 2, which is exponent multiplied by a constant that the program is going to estimate, but that it's applied only when the occasion is equal to 2, multiplied by exponent another coefficient when basically the occasion is equal to 3, and the same with occasion 4. Suppose, for example, that you want to know what would be an occasion 1, the average volume across the population. Then occasion equal 1, it's not 1 here, then it cancel. If 3 is not 1, it cancel. 4 is not what it cancel. Then all this disappear. And you are left only with the between subject random effect. But if I'm talking about the average, then this also cancel. Then for occasion 1, the average value of the volume of this one will be TVV. Now let's just do the same thing and let's just assume a different scenario. Suppose I want to know what's the average volume for occasion 2. Then that's the typical value. Average, which means that this cancel. And then now occasion 2 is not occasion 3, this cancel, and this cancels, and you are left with basically TVV multiplied by the effect of the occasion 2, which shift the average volume of distribution by this factor exponent A2. So fine. Then you can use this equation and you can basically write different scenarios depending on what you have. If I didn't have any fixed effect, if I didn't have any formulation effect, and only between subject to random variability, I would be left only with this product. And that's basically the equation that includes all the fixed and random effects that are applied for this example. Okay? Now you can stop. And stop sharing. Then all what we did here, it was just to practice a little bit all what we learned together on the first session. And once you are going to write the code with RNLME, then at least you will see that it will use exactly the same terminology. I mean, maybe instead of V is going to be written eta B. I don't know exactly what's the code. But if it's coming from a Phoenix and NME, then you would use a TVV and NV, etc.
Thank you, Serge.
You're welcome.
Arun, do you want to move us to the next question?
The questions are
Oh,
done.
we're done. We're done with the questions.
Oh, so Serge, do we have any? Oh, sorry, Arun. Do you want to check if there is anything in the chat that we have to address? If not, I know Serge wanted to present the next topic.
Yeah, just give me a moment.
So I also wanted to share that in all of you should be part of a group, and if any of you have not had a conversation, or if you're not heard from the group that you're part of, please let us know. As we had discussed on day one of the workshop, all the participants have been divided into groups.
We cannot hear you, Aruna.
Okay, my internet may be unstable here, so I'm going to wait for Arun to take us further.
No, it's just the volume. The volume. I mean, I cannot hear you well. I don't know the volume.
Can you hear me now?
Yes, but it's less strong than it was before. I don't know if somebody can tell me it's the same.
Yeah, the voice is a little feeble.
Yeah.
Oh, we don't have any additional questions at this point, Serge.
Okay, okay. Then let me share my screen, and then let's continue. And I'm going to go fast. I just want to address, just explain a little bit some concept, and then we are done for today. Then basic. Oops. Okay. Yeah. Okay. You can see my screen. Yes. Then
yes, we can see.
we talk about pharmacokinetic, and now we need to talk about basically about pharmacodynamics, which is basically quite similar to pharmacokinetic. Then, by definition, the pharmacodynamics is the study of the physiological effect of drugs in the body on microorganisms or parasites within or on the body, and the mechanism of drug actions and the relationship between drug concentration and effect. And for us, basically, we have data and we want to link basically response to exposure. Usually the response, that's a pharmacodynamic endpoint. In general, it can be a biomarker, it can be a surrogate, it can be also a clinical endpoint. When it's a clinical endpoint, it starts to be more complicated because the clinical endpoint, most of the time, are not continuous. And here today, we are just going to talk about continuous response, which is easier to handle.
Sorry.
And in the next, yes.
Sorry, I just wanted to interrupt you there for a second, because the screen that you're sharing, we actually see a split view and not the not the presentation mode.
Once again, we got it. I cannot hear you. What do you say?
So what I was saying was that
It was not the presenter view. Yeah, yeah. Can I give the? Yeah, we are seeing two screens. This screen and the next screen. It's basically the presenter view.
Ah, you do not. Ah, okay. Oh, okay. It's because I have a big screen having black.
Yeah, something because of these two screens, something's happening.
Yeah. Then how should I handle that?
No.
No. Let me see. Screen. Let me see 1 second. I can handle that.
Somebody's screen. So there is a display button is there on the top.
Okay. I remove the big screen and let me see. Okay, slideshow.
Yeah.
Can you see now?
Yes,
yeah.
Correct.
I removed the big screen. Apparently, there's some issue. Okay, then the pharmacodynamic explore what a drug does to the body, where the pharmacokinetic explore what the body does to the drug. That's something that you know. What I'm interested is to talk about how we model in general pharmacodynamic. I mean, the standard. We are just going to talk about some turnover. Then usually when you talk about turnover, let's just talk about, for example, C-reactive protein that we have in the body. And if we don't do nothing, if we don't give a drug, then most of the time we are going to see that there's a biomarker at the constant level. Then you could say, okay, if it's a constant level, then nothing's happened. But in fact, usually there are two processes that occur at the same time. The body is making the CRP, and the body also is removing the CRP. And when you don't see any change with time in the level of the CRP, it is because there's two processes that occur at the same speed. In other words, the rate of production of the biomarker is equal to the rate of elimination of the biomarker. When you are in such a situation, we say that we are in steady state. Now, what is going to break the steady state? It's when we are basically going to add the drug. And suppose that the effect of the drug is to decrease the production of CRP, then what you are going to see, you start at steady state and you are going to see that the level of the biomarker is going to go down up to a new steady state value that basically you are going to estimate using U model. Then that's the difference between steady state versus non-steady state. When before you give the drug, you assume most of the time that your biomarker is at steady state, and you break your steady state by adding suddenly your drug that is going to affect, is going to decrease the production of biomarker, and then you are going to get a decrease in the level of your biomarker. Now, that was usually what that's basically, it's called an indirect response model, and we are going to talk about that. But let's just talk about the difference between direct and indirect response, between pharmacokinetic and pharmacodynamic. When the change in the biomarker, or if you want your PD marker, is synchronized with the change in your concentration, we say that we have a direct relationship between PK and PD. And an example, it's for example, the well-known Emax model is equal to E0 plus Emax multiplied by C plus EC50. And if you have data, when you deal with real data, and if you see suddenly that you have synchronization between PK and PD, then you are going, the best is to start with a direct PK-PD model. Now, the indirect response model usually are linked to what I just explained before, where we have the biomarker with a turnover, and then the drug is going to break the turnover. But it takes some time until you see the effect. If, for example, you have an IV route, which means that you start at a high concentration and then the concentration decrease, You are not going to see the maximum effect immediately at t equals 0 when you have the maximum concentration, because it takes some time for the effect to show up. And what you are going to see, you are going to see that the PK decrease and the PD basically start to kick in. If, for example, the effect is to increase the production of a biomarker, you are going to see that when the concentration decrease, first, the concentration of your biomarker is going to increase. Now we need, when we do modeling, we need to write down some equation. And you have 4 well-known equations that are used to characterize the most important processes that we are dealing with in pharmacometrics when you are dealing with continuous response like biomarker. First, if you write the equation, if you write the equation for your biomarker without the drug, usually we assume that the production of biomarker, it's a zero-order process. It's called K-in. What does that mean, a zero-order process? It's a process that doesn't depend on anything else than just itself. It's a constant. It's like an infusion. Then K-in is, for example, you are making 1 mole of biomarker per hour, and that will be your K-in. The units will be the amount divided by time. Then now we have what is called the first order process of elimination of biomarker. Why it's called the first order process? It's because the elimination of a biomarker, the elimination of E, is proportional to E itself. And the coefficient of proportionality is K out. And then you have this famous equation dE dt is equal to K in minus K out multiplied by E. And dE dt is the change in the biomarker over an infinitesimal change in time. That's what it's called the derivative. It's a dE dt. And you're going to write this kind of equation when you are going to learn how to code this kind of model. Now, differential equation require initial condition unless the amount is equal to 0 at equal 0. In other words, your response, which is called E, if it's not 0 at equal 0, you need to write down what's the equation. But if you know that you are at steady state, it means that there's no net change, which means that the change in E with T, dE dt, is equal to 0. But before you give the drug, I just told you that basically we are at steady state, which is d dt, which is equal to K in minus K out, multiplied by E is equal to 0, because there's no net change in your response with time. Then if you get K in minus K out multiplied by E equals 0, you can take out the value of E, and you get E is equal to K in divided by K out. Remember one thing, writing down E equal K in divided by K out is correct only if you are at steady state. Now, many systems do not start at steady state. In that case, instead of writing E equal K in divided by K out, you will write E is equal to the baseline, and the program is going to estimate your baseline. Non-steady state occur, for example, when you go from one drug, the gold standard, and then you shift from one drug to the other drug, and the effect from the previous drug didn't go down to its steady state value yet, the value without drug effect. And then you give suddenly the second drug, and when you start, you still have residual effect from the previous drug. In that case, you cannot write K in divided by K out, but you write baseline, and the program is to estimate the baseline. Now we have 4 equations that are important, that usually you should have this in the library. I don't know exactly how an LME is going to be coded, if with library or without library, but if you don't have a library, you just need to write the differential equation. You can basically have either inhibition of the production, which is inhibition of the K-in, stimulation of the production, stimulation of K-in. You can have inhibition removal, in other words, that you inhibit the elimination part, or you can stimulate the elimination part. And you can see here, I write the 4 equations. There are 4 linked to an Emacs model, but that's a little bit different. You can see d dt is equal to K in multiplied by 1 plus Emacs multiplied by C divided by C plus C50 minus K out multiplied by E. Pay attention that when C equals 0, you come back to the K in minus K out multiplied by E, which means that you come back to the same situation that you were before you give the drug. It doesn't mean that immediately you are going to get the effect that you got when before you start giving the drug, because it takes time again to wash out. But if you concentration goes to 0 and you wait enough time, you are going to go back to the steady state that you had before you give the drug. And what is interesting in this equation is that it will start at the steady state level, K in by K out. And when you completely wash out the drug, at the end is going to go back to the same steady state. Now, if you give an infusion, for example, and you do not stop the infusion, at some point, you are going to get the level C that is not going to change. And now what will happen is that the production will be equal to K in multiplied by 1 plus E multiplied by C that doesn't change, divided by C plus EC50 that doesn't change, EC50 is a parameter. And then your new production doesn't change, it's equal to this value, the K in multiplied by what is written in red. Then you reach a new steady state level, which is equal now, again, this is equal to 0. And then what is your new steady state level? It's K in multiplied by 1 plus E max multiplied by C divided by C plus EC50 divided by K out. And now you understand what is E max. E max is the maximum fraction by which you can increase your steady state level of your PD marker. EC50 is the concentration that will lead to half of E max, same traditional definition of EC50. Now, if we go with the same principle and we shift to the second kind of indirect response model, it's the production inhibited eliminated, which means that the production is inhibited by the concentration. Then it's a 1 minus I max. Now, instead of E max, we write I max just because the I is the word inhibition. Inhibition starts with the I, and that's why you put I max. No other reason. Okay? Can put any name. Now, I max must be between 0 and 1 because I max is the maximum fraction by which you can decrease the production of your biomarker. And IC50 is a concentration that will give you I max divided by 2. Okay? Then it's very similar equation. It's more difficult to handle inhibition than stimulation, but that's another issue. For all there's a 2 scenario, the same initial steady state condition apply, which means that the biomarker is equal to K in divided by K out. Okay. Now the 2 other one basically concentrate now on the second part of your model, which is the elimination part. And again, you can stimulate the elimination, then the biomarker is going to be removed faster. Then it's a 1 plus E max that you put now in the K out part. Okay. What is red is what was not before we gave the drug. Okay. And then the second part, it's very similar. It's symmetric to what I wrote before. Before it was on the left side, and now it's on the right side, the second term. And you can have inhibition of the removal, which means that it will be more difficult to wash out. Many times we have what is called identifiability issue, is because the net effect of stimulation of production or elimination or inhibition of the elimination will give you the very similar results. Then most of the time you need to speak with experts that can understand the mechanism of action, can tell you know what, that's what the drug is doing. It affects the production and it affects the elimination. Because if not, it's difficult to separate, to know if what we have with real data is due to something that happened at the production level or at the elimination level. And same thing, the same initial condition. Now, sometimes also when we are not talking about biomarker, but for example, we have the drug and the drug has to go to some tissue, and that's why you have the effect. Then the delay between PK and PD is due to the fact that the drug has to go to somewhere else that we hypothetically define as an effect compartment. An effect compartment, it's not something physiological, but if you put an effect compartment that it's linked to your central compartment, your plasma compartment, and you assume that the effect occurred there, the Emax model will occur there, then you are going to have also a delay between PK and PD. But most of the time, again, you need to understand where it's coming, where the delay is coming from. when you talk about biomarker, most of the time it's an indirect response model. When we talk just a regular drug that affect basically your PD by going into a tissue compartment, and there you have a direct relationship between the concentration in your tissue and the effect, then effect compartment linked to a direct relationship between the concentration in the effect compartment and the PK is the right things to do. And how we write down that, we are going to learn that when you are going to learn the PML. We assume first that in the effect compartment, we have an equation. CE is the concentration in the effect compartment. And we assume that basically this effect compartment is getting input from the central compartment, plasma compartment, with a rate KE0. And we assume the same rate. And we have an elimination with the same rate from that effect compartment. Then that's the equation that usually we use for the effect compartment. And K0 is the first order effect compartment with constant that we are going to estimate. Now, what is interesting is that now, basically, you have your PK model, you have a model that links the effect compartment to your PK model, because C is the concentration in the plasma compartment of your PK part of the model. And now you assume a direct relationship between the effect, but the concentration in the effect compartment and not the concentration in the plasma compartment. Then the delay or the desynchronization between PK and PD will be shown here because the concentration in the effect compartment is delayed relative to the concentration in the plasma compartment. Again, it takes time to go from the plasma compartment to the effect compartment, and then you are going to see a delay. Now, sometimes what can happen, and again, you need to work with data and with the expert, you can have a combination of indirect response model and effect compartment, but it's quite difficult to handle this kind of model. In other words, it takes some time to go to the tissue, but the PD is a biomarker. The biomarker has turnover. Then you have the turnover process, but you have the turnover process like here. But because the regressor that it's linked to basically the elimination of your biomarker is not C, but could be CE. Then you could have basically the same model here. In other words, let me see the simple example. For example, the product, you have production, you have increase in the production of your biomarker, but that doesn't depend on the concentration in the plasma compartment, but could be depend on the concentration in your effect compartment. Then you would have basically the two differential equations. This differential equation, instead of C, you would have CE. It will be combined with this differential equation for the CE. Okay. And then you would have basically, there's a two differential equation, and you would have basically the Emacs model that's embedded here. Here. Then the only things that you would have if you have the combination of indirect response model and effect compartment is instead of C, you would have CE. Then if you don't have an effect compartment, you have your PK model and you have your PD model. If you have an effect compartment, you have your PK model, you have your effect compartment that lead to CE, and then you have your indirect response model. And that's basically in a simple word, the difference between indirect response model versus effect compartment. About when to use what, I would really rely on the expert that they explain what drug are we talking about and what biomarker are we talking about. When the apparent delay between the drug concentration and effect is due more to a lag in PD process than biophase equilibration, indirect or turnover PD set may be more appropriate. Turnover models are best conceptualized when the effect is an endogenous biomarker, and that I explained like CRP. For example, serum creatinine level at any given time is the net balance of production via breakdown of creatine phosphate in muscle and removal via glomerular filtration. Then if you understand the clinical pharmacology, and I'm pretty sure that I have many experts in clinical pharmacology, you can by yourself differentiate between the kind of PD model that would be more appropriate. And sometimes you can have both an effect compartment model and turnover model may fit a given data set equally well. And the choice between the two may need to be made on mechanistic grounds. But again, from my experience, it's not always easy to use them both together. But usually what you do, you first write a direct PKPD model. And if it doesn't work, then you go to the indirect response model, unless you know that there's no way that you are talking about turnover processes. And then you try to add an effect compartment. Again, this is just the basic background information that I'm sharing with you. Once you have data, everything is different. Then when you do population PKPD, the best method would be to do a simultaneous fit. What does that mean? In other words, you take your PK data and you take your PD data all together. You have two models. You ask the program to optimize to find the parameter at the same time for PK and PD, and then you are done. Another way to do it, which in practice works better, but from a statistical point of view is less correct than the simultaneous fit. It's a sequential fit, and I would suggest you in my cookbook I explain that you always start with sequential fit. Once you in the sequential fit, what you do, you first feed the PK model to the data, then you find the population PK characteristics. From the population PK characteristic, the program, any program will give you also the Bayesian estimate, which are the individual PK parameters for each individual. You plug the individual PK parameter into your PD model, and you do not estimate anymore the PK part of the model in the PD fit. In other words, PK, it's completely known for each individual. It's just an equation that you use, and you put the parameter for each individual, the PK parameter for each individual. And then you feed the PD model to the data, given the individual PK that are known. Then from a maximization, optimization point of view, you just need to estimate the PD parameter and not anymore the PK parameter. Then you could ask me, yes, then why not doing a sequential fit all the time? The reason it's statistic is that when you put one value, if for example, individual number one, it's a one compartment model, the volume is 50, his volume is 50, his best volume is 50, and his clearance is, let's say, 5. The truth is that for each individual, there's no only one value associated with that individual. Each individual has its own, what is called, if I'm telling you the value is 50, in fact, the optimal value for that individual is 50. But maybe with less chance, it could be 49, it could be 51, 52, 48, 46. When you use the population approach, the program accounts for the fact that we have a distribution of the volume for each individual. Not just a distribution for the population, we have what is called the individual distribution, or what is called the individual conditional distribution for all the parameters. When you do the sequential fit, you just took the best value of the volume for each individual. Then you lose a little bit about the variability in the volume within the same individual that basically is not accounted for. In practice, when you have very rich data, then it's really negligible because you know very well the volume for each individual. There's not so much room about what other value you could get for that individual. In other words, when you have very rich data, the sequential fit is going to work very well. The strategy that you could use is start with a sequential fit. You start basically, you do the PK, you get the individual PK estimate, then you go to the sequential fit, you do the PD, knowing the PK for each individual. When you are done, now you have the PK characteristic from your first fit, you have the PD estimate, and now you do simultaneous fit where you start with the best estimate for the PK you got from the PK first, and the best estimate for the PD when you did the sequential fit. And then you try to do simultaneous fit. Then again, the approach, the cookbook that I wrote, tell you to start with a sequential fit and then try the simultaneous fit. The reason why starting with simultaneous fit doesn't work always, for many reasons. Sometimes you can have a PD contamination because of the PK. The PK is really problematic. And then you have a lot of noise in the PK, and then you try to estimate the PD parameter simultaneously with the PK, then what's happening is that the program that doesn't differentiate between PK and PD, just see parameters, is going to basically give you at the end a bad PK fit and a bad PD fit, because the PK was so bad. And that's why it is better sometimes to do a PK fit first and then a sequential fit. Now, about what we are looking for when we do a PD is the same approach. We have the fixed effect, we have the random effect between individual and between occasion, covariate model and error model. Then PD is just a name. And if we know the PK for each individual, then the PD approach, the PD cookbook is exactly the same like the PK cookbook. Now, about the hysteresis, what's happening is that if you have an indirect response model, then what's happening is that the relationship between the drug concentration and the effect being measured is not a simple direct relationship, but may have an inherent time delay. Because of the time delay, suppose that you have an absorption drug, then the concentration is going to increase, then decrease. And then suppose, but then it takes time for the effect to kick in. Then what will happen is that you are going to see a sort of hysteresis. In other words, when we look at the PD on the y-axis, and the PK in the x-axis, then the last two plots show you basically the hysteresis. In other words, that if you do a cross-section at a specific drug concentration, you are going to see two values of PD. And when you plot your data, even your observation, and if you know the PK and the PD, you can have some insight about if we have hysteresis or not hysteresis. The second plot show you just the gamma. In the Emacs model, you can have what's called the Hill coefficient that can affect. But the first two has no hysteresis, and the two second has basically an hysteresis. Then I think that we are done for today, because next week I want to introduce basically the categorical response. I will give also an update of the slides, because I add, Harun, I add some slides about the likelihood. Then I will need to send you that, okay?
Sure, thank you, Serge.
You're welcome.
Serge, will there be any homework on this particular section that you have covered?
No, this was just an add-on, because we had time. But the homework will be after the next session, where we'll introduce the categorical response, time to event, and COM data.
Sure. Thank you again, Serge. Thank you for and if you can send the updated slide deck for the next session, we would actually share that.
Well, I will send you an update of the full slide.
Sure. So any questions that anyone has with what we covered this morning? I think Nilesh, do you have a question? Let me unmute you.
Yes. Hello.
Go ahead, Nilesh.
Yes. Thank you, Serge. Again, it was really a good presentation on PKPD. My question is about effect compartment. Since we are adding the effect compartment and the Emacs model is linked to the concentration in the effect compartment, the EC50 that we estimate, how it correlates with the plasma concentration?
It's not correctly. Yeah, it's like a hypothetical. I mean, again, if you look at the equation, you can answer to that. Let me show you. Then basically you're talking about this equation, yes. Then yes. Basically the EC50 is the concentration in the effect compartment, in the hypothetical effect compartment that linked to the half of the Emacs, and not from the plasma compartment.
So generally we have concentration from the plasma. So the EC50, can we?
No, you cannot. Yeah, that's the question, because the EC50 is related to the effect compartment. This is just pure mathematics. If you basically take EC50 equal to basically the concentration that lead you to half of the, if CE is equal to EC50, if the concentration in the effect compartment is equal to EC50, then you get basically half Emax. But you then you can know what's the concentration in the effect compartment that that lead to half Emax, and then from that concentration you can look then back what's the plasma, the corresponding plasma concentration.
Okay. Okay.
You have to do it basically sequentially.
Okay.
But again, you need to be careful again of the hysteresis and all this.
Oh, yeah.
I mean, it's a very good question. And what's happening is that when you have an effect compartment, the definitions start to be more complicated because it's not related directly now to the plasma levels.
Yeah, yes.
Then the interpretation is really different, because suppose that you have an IV model, an IV route, then what will happen is that you are going to see the concentration that decrease when the concentration in the effect compartment increase. Yes. Then what is EC50? Then it starts to be contradictory. I mean, what does that mean? That a low concentration in the plasma, it will be EC50, and that's more difficult to understand. But what's happening is that when the concentration in the plasma compartment going down, the concentration in the effect compartment is going up, and that's you basically your marker that it's linked to the EC50.
Yes, yeah.
Thank you, Nilesh, for the question. Any other questions from your end, Nilesh?
Yes. So if we consider the free drug hypothesis and considering the free concentrations are same between the effect compartment and plasma compartment, can we then assume that the EC50 can be correlated with the, or it can be related with the plasma concentration, like convert the free concentrations and then to the total plasma concentration?
I'm not sure that I understood the question. You said that if we say that the concentration in the effect compartment is equal,
free concentrations are equal in plasma and the effect compartment, if with that hypothesis.
The free? Did you say free?
Yes, free concentrations.
But are we talking about binding process?
Yes, if we consider free drug hypothesis, we generally assume that the free drug in plasma is and the other tissues are equal, the concentrations are equal at the steady state. So with that hypothesis, if we assume that the free concentration are same between the effect compartment and the plasma compartment, can we then say that or convert that free concentrations to the total concentration in plasma and then calculate the EC50 in plasma?
I mean, I guess but my question is that in the equation C, is C the total concentration or the free concentration?
Yes, basically then we need to convert the concentrations to free concentration, but then it is not an effect compartment.
Okay. Yeah, then I don't know exactly basically what you should do. I mean, once you know the assumptions, then you can just plug that into your model, and then you will know the answer. But if C is the free concentration, then you do not have a delay, because you assume that the free is equal to the free concentration in the plasma is equal to the free concentration in the effect compartment. You don't even need an effect compartment. Now, if C is the total concentration, then that's a different story. You still have a delay.
Okay. Yeah. Yeah. Thank you.
No. Any other question?
Thank you. Thank you for that. And my apologies, my internet disrupted my conversation. conversation here. So, so previously, can you guys hear me well?
Yeah, yes.
Yes, Aruna.
Now we cannot hear you. I mean, I cannot hear you.
No, we cannot hear her. I think her internet issues. So, yeah, this is what planned for today, right? Search. You've done.
Yeah. Okay, I'm done, and apparently we have some internet issue. Then I think that if there are no other questions, I think that we can adjourn for today.
Yeah. So, yeah, that's fine. Thank you, Serge, for the interaction with, and walking us through the answers for the previous homework, and then walking us through pharmacodynamic models. I know other people might be feeling pharmacodynamic model as little more, concepts and explanations in it. After Serge is sharing the slides, please go through them. Also go through some general literature, and you should be able to understand. And definitely in the group discussions, we can surely discuss about these concepts as much as possible. And then definitely it's not a single day you will understand all the concepts. It takes so many years of experience is sharing in such short time. There are papers, other type of materials are with us. We'll share, and we'll continue discussing in further group meetings. Okay. I think if there are no questions, I think we can proceed to Serge.
Oh, okay. Okay. Thank you very much. And then see you next week.